We're going to be working through example C. Example C says a chemist adds 41.56 milliliters of 0.25 molar NaOH to 25 milliliters of H3PO4, also known as phosphoric acid, to neutralize it. What is the concentration of phosphoric acid that you need? So first of all, as with every stoichiometry problem, you need to establish what the chemical equation is. So having said that, we know that we have NaOH, sodium hydroxide, and remembering NaOH, Na has a positive 1 charge, OH has a minus 1 charge, so they can match up 1 to 1. We know that this is a base and also that it's aqueous. It's going to combine with phosphoric acid, which we're told is H3PO4. And just a reminder, the 3 for the H is because phosphate, which is the ion, has a negative 3 charge, and that as well is aqueous. So we know that this is an acid-base reaction because OH is an indication that we've got a base, and the H, anything that starts with an H, is an acid. And so an acid-base reaction always forms water. So we know that we're forming H2O in liquid form. And then the other combination we have is sodium phosphate. Now don't forget that phosphate has a minus 3 charge, and for that reason we need to have 3 sodiums so that all of the ions can get a full valence shell. When I look at my solubility chart, I see that it is soluble, so we write aqueous. The next step is to see whether or not this equation is balanced. Remember, we always start with every chemical other than carbon, hydrogen, and oxygen. So I'm going to start with the sodium. With the sodium, I see that I have 1 sodium here, 3 sodiums there. I'm going to place a 3 in front here, so we have 3 sodiums going into the reaction. Next, I'll be looking at the phosphate. It looks like I have 1 phosphate on this end, 1 phosphate on that end. That works out fine. Let me take a look at now the hydrogens. So I have 3 hydrogens here, 3 here. That means I have a total of 6 hydrogens, but on this end I only have 2 hydrogens. So if I place a 3 over here, that gives me those 6 hydrogens. Lastly, we'll look at oxygen. I have a total of 7 oxygens on this end, 7 oxygens on that end. That tells me that my equation is balanced. The next step is to identify my A and the B. Remember, A is my given. A can be anywhere on this equation. I can even have A as the products, and I can have B as the reactants. Don't think that A has to be in the reactant side and B has to be in the product side. They can be anywhere. A simply means this is all of your given information. And in this case, my given information is sodium, so this is going to be my A. Next, I'm going to, excuse me. Next, I'm going to take a look at what my B is. My B is my phosphate. So let's start identifying what it is that we have for A. It tells me we have a volume of 41.56 milliliters. We can also write this as 0.04156 liters. Remember that we like to work with liters because we are usually working with molarity. I'm also told that I have a 0.25 molar solution. I can also write this as 0.25 moles for every 1 liter is my concentration. The reason that I like to write it this way is that it allows me to start canceling things out. I'm also told that I have a volume of 0.025 liters, or 25 milliliters of phosphoric acid. So what I need to do is I need to determine what concentration do I need to have in order to neutralize this. So what we're going to start off with is our schematic. And you're going to have to refer back to your notes for that. But once you look at what we have in our A, we know that we have volume A, And from volume A, we can manipulate molarity A. Yes, you will always be given these two. And that gets us to mole A, which then gets us to mole B. And at that point, we're asked for what is our molarity. That is our unknown. So our schematic tells us that after mole B, we get to molarity B. Okay, so let's go ahead and set up our dimensional analysis. We know that we have 0.0415 liters of NaOH. We want to cancel that out, and we can do that by using the molarity. And the way that we want to address molarity is as a fraction. That allows us to cancel things out. So we have 1 liter of NaOH over 0.25 moles of NaOH. And it's important to check whether or not these cancel out. They do. Next, we've already taken care of our molarity A. It gets us to the answer of mole A. So we now need to look at the relationship between mole A and mole B. And when I look over here, it looks like it's a 3-to-1 ratio. That means that for every 3 moles of NaOH, it requires 1 mole of H3PO4. Again, I check whether or not these cancel out, and they do. So that got me to mole A. So now I need to get to molarity. Now this one is a little bit unique in that you're going to notice that I now am at moles. And remember, molarity is moles over liters. Now take a look what I have up here. I already am told how many liters I have. I am given the units of moles over here. So essentially all I need to do is I need to calculate this through, which is 0.003463 moles of H3PO4. So I know that's how many moles I have. And I simply place that into my equation because I also know how much volume I have. So I write 0.003463 moles of H3PO4 over 0.025 liters. And that answer gets me, if I do my significance figures, to 0.14 molar H3PO4. So let me review this step again of why I did this. I'm looking for molarity. I know that molarity is moles over liters. When I do my dimensional analysis, I recognize that at this point right here, I can answer my question of how many moles I have in the solution or that I need. I'm also told, thanks to the question, that I am given 25 milliliters. So if I know how many moles I have and I know how much volume I have, I can simply divide the two together to get the molarity.